Two plates, perfect conductors, uncharged. Seemingly, there is nothing going on between them. The gravitational attraction between the plates is infinitesimal. However, there is another force. Because of the effects of quantum mechanics, there is a strange and unobvious attraction between these two plates, the Casimir effect. Over the next 45 minutes, I will explain this effect intuitively and mathematically, give an overview of its history and applications, and discuss its implications for the whole of quantum mechanics and physics. So, what exactly is going on here? The attraction has to do with something called quantum vacuum fluctuations. To very briefly summarize, quantum mechanics shows us that we cannot measure things with absolute perfect precision. Exactly zero is actually a perfectly precise measurement, so according to quantum mechanics, electromagnetic waves cannot actually have zero magnitude. Instead, they have a non-zero minimum magnitude, and this essentially means that empty space, nothingness, is filled with tiny, ever-present fluctuations. When we have two conducting plates very, very close to each other, they interact with these fluctuations, and this produces an attractive force between the plates. One intuitive analogy that might help us understand this is to consider the example of two plates submerged in water filled with waves. When you have just one plate, waves from either side produce equal forces on the plate, so it doesn't move. However, when you have two plates close to each other, the right plate receives a force from, but also blocks incoming waves from the right, so those waves never reach and apply a force to the left plate. Similarly, the left plate blocks incoming waves from the right, so the right plate never receives any force from the left. Thus, both plates receive force from the outside, but they receive very little corresponding force from the inside. This means that they move toward one another. And we can see this in real life. This is a useful intuitive analogy. However, the Casimir effect isn't quite the same as two plates submerged in water. Let's take a closer look. Electromagnetic radiation can be thought of as a wave moving through space at the speed of light. Specifically, electromagnetic waves propagate through the electromagnetic field. The electromagnetic field is quantized. It can be thought of as the sum of those waves. Under a quantum mechanical treatment, these waves are quantum harmonic oscillators, and again, because of consequences of the Heisenberg uncertainty principle, their ground state energy is non-zero. The energy of the electromagnetic field in the ground state is the sum of many quantum harmonic oscillators, each with energy h bar omega over 2. These are quantum vacuum fluctuations. The zero-point energy, the ground state energy of the electromagnetic field, is the sum of practically infinitely many h bar omega over 2 terms. To derive this more formally, we have to look in detail at the quantization of the electromagnetic field, but that is outside the scope of this presentation. Yes, this essentially means space is filled with infinite energy. Even if we assume that zero-point fluctuations stop at certain very high frequencies or at a small enough scale, the Planck scale, the energy density of any random cubic centimeter of vacuum would be over 20 orders of magnitude larger than if you took the energy density of a cubic centimeter at the center of the sun and multiplied it by the number of atoms in the universe. In other words, the zero-point energy is very, very big. Why don't we see any evidence of this? Well, because of more consequences of the Heisenberg uncertainty principle, we also know that any waves from such quantum fluctuations would have extremely short lifetimes. and they would only travel a small little bit of their wavelength. This means that the quantum fluctuations are more wave fragments than full waves, and we don't yet have a very good way of interpreting this. A more detailed discussion of the reality of zero-point energy and zero-point fluctuations is given in the last section of this video. In any case, when we work with zero-point energy, we typically think of things in terms of relative energy, in terms of differences in energy. We essentially define the zero-point energy to just be zero, and then we work with that. But how do these quantum vacuum fluctuations and the zero-point energy create an attraction between two plates? How does that make sense? To answer this question, we're going to imagine two situations where we have a perfectly conducting plate and a hollow cube with perfectly conducting walls. In one situation, we'll place the plate inside of the cube very, very close to the wall of the cube, and in another situation, we'll place the plate about in the middle of the cube. The specific position of the plate in the second situation is mostly irrelevant. As you'll see later, the important distinction is that in the first case, we will say that the plate is so close to the wall that the length of the cube is arbitrarily large in comparison. In the second situation, the distance between the plate and the wall is on the order of the length of the cube, as in the distances are comparable. When we sum the zero-point energy between the plate and the wall when the plate is close, or when the plate is far away, the sum diverges. However, if we look at the difference in energy between these two situations and manipulate things with a cutoff, we can get a finite result, and we can interpret this as the Casimir force. When we look at this difference, we're looking at a relative energy. We're saying there is more energy in one situation than in another situation. So if there is no force in one of those situations, there must be a force in the other one. More specifically, because we have a perfectly conducting cube and a perfectly conducting plate, all electric fields disappear on the surface of the cube and plate. This means that the only quantum vacuum fluctuations that can occur between the plate and the cube are standing waves that are zero on the surfaces of the objects. Waves that move would be non-zero at the surface of the objects during certain points in time, and this would be impossible. This means that only certain frequencies of standing waves can quote-unquote fit between the plate and the cube, because the waves must be zero at the surfaces of the objects, because the objects are perfect conductors on which all electric fields dissipate instantly. There certainly are frequencies that can fit between the plate and the cube. All frequencies that have nodes at the surfaces of the object can exist, and for each situation, there are an infinite number of these frequencies. In fact, these are the quantum vacuum fluctuations that exist in these situations, and we can calculate the zero-point energy for each situation by summing up the energies of these fluctuations. However, there are essentially less allowed frequencies in the first situation because the plate and the wall are so close together. Again, in both cases, we will still get an infinite amount of energy if we try to calculate it, but if we subtract these two situations and use a cutoff, we can get a useful result. The reason there is a difference in energy here is because the plates are really close together in the first scenario, as we just discussed. This constrains the allowed frequencies of the fluctuations more in the first situation than in the second situation when the plate and the wall are more distant. Particularly if we take the cube with the plate in the middle to have zero energy, that means that between the cube and the plate, when the plate is very close to the wall, there is negative energy relative to the situation where the plate is farther away. This difference in energy essentially applies a pressure to the plate. Force is the gradient of potential energy, so there is an attractive force between the plate and the side of the cube in this situation. Let's derive this mathematically. We will say that the perfectly conducting hollow cube has sides of length L, and we will imagine that the plate also has sides of length L, and the plate is aligned with the XY plane. In the case where the plate is very close to the side of the cube, it is at a distance A. In the other case, the plate is still at a distance a, but this time a is on the order of L over 2. To calculate these energies, we have to figure out the allowed wave numbers of the vacuum fluctuations in each situation. Remember again that our objects are perfect conductors, so the tangential component of the electromagnetic field must vanish at the surface. Technically speaking, our objects are imposing Dirichlet boundary conditions on the electromagnetic field, and the most principled way to derive the allowed wave numbers would be to solve the wave equation with those boundary conditions. However, that formal derivation is outside of the scope of this video. Instead, we can reason a little bit about the geometry that is going on here. Specifically, we can realize that the wavelengths must be factors of the distance between the plate and the box, because otherwise the corresponding wave would be non-zero at the surface of the object. The wave number is the reciprocal of the wavelength, so we can find that the wave numbers are multiples of the reciprocal of the distance at hand times pi. For example, if we were calculating the wave numbers that can fit inside the cube, we'd find that they are n times pi over the distance, L. So, between the wall and the plate, the allowed wave numbers are an integer n times pi divided by a, in both cases. This is slightly confusing because you'd expect that in the second case, we'd use the distance L over 2. Moreover, if we're going to be subtracting these and using both of these a's in the same expression, how will we distinguish between them? This seems rather contradictory. As you'll see in a moment, the way we're going to be distinguishing between these two is a bit more subtle. Because in the first situation, L is arbitrarily large compared to A, we can treat L as essentially infinite and A as essentially infinitesimal in the first situation. And that also means that A is also arbitrarily large in the second situation compared to A in the first situation. Because the allowed wave numbers have a term of the reciprocal of A, if A is very, very big, we can actually treat the allowed wave numbers as continuous. We can imagine that as A gets bigger and bigger, the distance between each allowed frequency gets smaller and smaller. We can extrapolate this to when A is arbitrarily large, and we realize that we can, in fact, treat the allowed frequencies as a continuous spectrum. This means that when A is arbitrarily large, we can treat K as a continuous variable and integrate across the spectrum of allowed frequencies. Conversely, when A is very, very small, we definitely cannot treat K as a continuous variable. Remember, the allowed wave numbers have a 1 over A term, so the allowed wave numbers have comparatively large gaps between them when A is small, so we have to sum over discrete values in that case. However, unfortunately, there are 3 dimensions, so we also need to calculate the allowed wave numbers in the x and y direction. Since the plate is aligned with the xy plane, there's nothing that ever blocks the waves in either of those directions besides the walls of the cube. That is to say, the walls of the cube are the only things imposing boundary conditions on the electromagnetic field, so the allowed wave numbers in all cases in the x and y directions are the same as the allowed wave numbers we calculated earlier between the walls of the cube as an example, n times pi divided by L. Now, to calculate the energy, we have to sum up the energies of these waves. In a vacuum, we can express omega as the speed of light times the wave number. And we can find this expression. This square root term is the total magnitude of the wave numbers across all 3 dimensions. However, we can't exactly just calculate this sum using our different sets of wave numbers and try to subtract things. The sum diverges. Instead, we have to figure out a way we can subtract things and still get a meaningful result. The way we can do this, as discussed earlier, is by assuming L is arbitrarily large. We'll start with the case where A is arbitrarily small compared to L, when the plate and the wall of the cube are very, very close together. We'll expand our summation in all 3 dimensions for clarity. Next, we'll convert 2 of our summations into integrals, Here, we are treating nx and ny as continuous, and we can do so because we are taking L to be arbitrarily large. However, we cannot convert the summation corresponding to nz into an integral because the wave number kz has a factor of 1 over a, not 1 over L, and so the quote-unquote distance between wave numbers is certainly not arbitrarily small. We'll make substitutions for kx and ky, and this will introduce an extra factor of L squared over pi squared in front of our integral. This is one instance of L over pi for each of the two substitutions we're making. Next, we need to examine our bounds for a moment and account for something called wave polarization. For each k, there are actually two possible directions that the corresponding wave can face. When we were summing, we summed including negative values of n, but here we're going to integrate from 0 to infinity, so we have to multiply our entire result by 2. However, multiplying our entire result by 2 actually double counts the mode when nz equals 0, so we have to introduce this special notation at the bottom of the summation. This 0,1 expression indicates that the case when nz equals 0 should be multiplied by 1/2. This special case arises when we essentially fold over our expression from summing including negative values of k to summing from 0 to infinity, and happens because there is a discrete case where nz equals 0 in the summation, which is not true in the same way when we are integrating. And unfortunately, 0 and negative 0 are not distinct. Next, we're going to introduce polar coordinates in the kx-ky plane to further simplify our expression. We're only going to integrate radially from 0 to pi over 2, that is, in the first quadrant. This is because kx and ky are only both positive in the first quadrant. We already accounted for negative values of these wave numbers previously, so to avoid double counting those modes, we must only integrate from 0 to pi over 2. After substituting polar coordinates and evaluating our radial integral, we get this expression. As the final step for the case where the plate is very close to the wall of the cube, we are going to switch the order of summation and integration. The reason for this will become apparent in a moment, but it is justified because we could have simply began with a different order of summation when we started. We will begin our treatment of the case where a is on the order of L over 2 in the same manner. The sum here is expanded into 3 dimensions for clarity. However, this time we can treat all 3 wave numbers as continuous because since a is on the order of L over 2, it is arbitrarily large, and the distance between frequencies with the 1 over a term is essentially infinitesimal, so we get 3 integrals. We can substitute in kx, ky, and kz again for our n's. This time, the substitution introduces a factor of L squared a over pi cubed. The extra term of a over pi as compared to last time, of course, comes from our substitution for kz. Because we are once again integrating from 0 to infinity, we have to account for the wave polarizations, the negative values of k. This time, since we just have 3 integrals, there are no special cases, and we just have to multiply our entire expression by 2. As in the previous case, we're going to substitute polar coordinates in the kx-ky plane. For the same reasons as last time, that we're only concerned with positive values of kx and ky, we must only integrate radially from 0 to pi over 2. After evaluating the radial integral, we can find this expression for the energy between the plate and the wall of the cube in the case where they are arbitrarily far apart. Now we must subtract. Our energy difference is given by the energy when the plate and the wall of the cube are very close together, minus the energy when they're far apart. Substituting in our expressions, we can find this. Note that we've written nz as just n for brevity. We'll factor all of the constants we can to the front. Then, to simplify this expression, we'll make the u substitution u equals the quantity ax over pi squared. Particularly, this will let us simplify the inside of the square root and let us factor out all of the constants multiplying n. We'll continue to simplify and factor everything to the front. We will also substitute n for our variable of integration in our second term. This gets rid of the extra a over pi term, and you'll now notice that we have a sum minus an integral of the same expression. This will become important later. For now, you may notice that our expression still diverges, and we need to fix this. We will multiply each of our integrands by a special cutoff or regulator function that will allow us to get a useful result. This function should behave such that for a wave number k, if it is significantly larger than a certain cutoff, km, then the function approaches 0. Conversely, if k becomes much smaller than the cutoff km, the function approaches 1. The precise shape of the function or the value of km are not important for this derivation. In this case, we do have a physical justification for multiplying by this cutoff function. Every conductor has a plasma frequency, where above the frequency, the electrons in the conductor can oscillate in resonance with applied electromagnetic waves, and this means that the conductor essentially becomes invisible to electromagnetic radiation above this cutoff frequency. At high enough frequencies, our boundary conditions fade. Now, after multiplying by our cutoff function, we can find this result. In terms of physics, we are done. Now we just have to evaluate our expression. We will make the substitution w equals n squared plus u to simplify, making sure to modify the lower bound of our inner integral appropriately. We will define the inner parts of our expression to be big F of n, so we can now see very explicitly that our expression is the difference of a sum and an integral of the same function. Both Euler and Maclaurin independently discovered a way to evaluate this kind of difference in 1735. In the Euler-Maclaurin formula, here bk is the kth Bernoulli number, and r is an error term which is small for sufficiently large values of p. We can now find and evaluate the first two derivatives of f, and evaluate them and plug them into the Euler-Maclaurin formula by considering the behavior of our cutoff function. Also, these first few terms are actually all we need. If we think about the next few derivatives, we'll realize that they all contain powers of pi over a km, and for sufficiently large km, they become vanishingly small. Thus, with just a little bit of simplification, our approximation of the difference in energy is actually complete. Our final result is a negative energy, but how does that make sense? Recall that we got this result by subtracting 0-point energies. It is more accurate to say that the 0-point energy in this situation is negative relative to the 0-point energy in free space than it is to just say we have a negative energy. Let's move on and calculate the resulting force. Force is the negative gradient of potential energy, but in this case we are only interested in the direction along A, so we can use a single partial derivative. We did manage to get through that entire derivation without dropping a minus sign, and we're finishing off with a triple negative. With our final approximation of the final force, it is trivial to find the force per unit area, or pressure, and this is our final result, what is called the Casimir force. This pressure, as intuition might suggest, is very, very small. For example, when the distance A is about 0.5 micrometers, we get a pressure of about 0.02 pascals. For context, standard atmospheric pressure is over 100,000 pascals and is almost 5 million times higher. As a side note, this technique of wrangling finite results from divergent sums or integrals, where we multiplied by a cutoff function, is called regularization and is widely used in physics, especially quantum field theory. In this case specifically, we do have a physical justification, the plasma frequency of the conductors, but in many cases, regularization is still necessary even when there is no obvious physical justification, but we have very good reason to believe that the new result we're calculating should be finite. In those cases, we often actually defer to unknown physics or say there will be new physics at different scales. We say we don't know how, but we know this thing is finite, and then we introduce a cutoff or regulator to make it finite. When we introduced our cutoff function f, we performed regularization. In quantum field theory, regularization is almost always followed by another technique that essentially helps justify what we just did, called renormalization. Renormalization in this context amounts to showing that the final result doesn't depend on the specific parameters of the cutoff function or regulator. We could do this by, for example, taking the limit of the cutoff frequency to infinity after already obtaining a finite result. However, we actually already performed renormalization in our derivation. When we applied the Euler-Maclaurin formula, we had to evaluate our function of big F of n at 0 and infinity. And this shows that the cutoff frequency km could range from 0 to infinity, and as long as the distance between the plates remains on a scale that doesn't interfere, we could get the same finite result, no matter the value of the cutoff frequency or the shape of the cutoff function. So we regularized and then we renormalized. Going back to our final result, you might wonder, how was this first discovered, and how do we know that it is true? In 1948, physicists Theo Overbeek and Evert Verwey conducted an experiment with colloids, and their results disagreed with the current understanding based on the interatomic potential determined by another physicist, Fritz London. According to London's work, the attractive potential between molecules was proportional to 1 over the distance to the 6th power. However, at larger distances, it seemed to disappear a little bit more quickly according to experimental measures, proportional to 1 over the distance to the 7th power. Overbeek thought of some potential explanations, and then he brought this problem to 2 other scientists, Hendrik Casimir and Dick Polder. Casimir and Polder used tools from quantum field theory and quantum electrodynamics and showed that in certain situations, an atom in an electromagnetic cavity with perfectly conducting walls will be attracted to the walls, and this is now called the Casimir-Polder force. I'd also like to note that they had to perform regularization and renormalization here, too. They introduced the cutoff e to the negative gamma k, and then performed renormalization by showing that the finite result remains when gamma is 0. This, of course, just makes the cutoff function equal 1, so it shows that the final result is independent of the cutoff parameters. They also did have a physical justification for the regularization, the variation of the electromagnetic field inside of the atom. In any case, they extrapolated their calculations into the more complicated scenario of the attraction of 2 atoms, and found theoretically that the potential indeed was proportional to 1 over the radius to the 7th power. The calculations they used to derive this result were quite convoluted, very long, and unwieldy. However, the final expression that they yielded, as we just saw, was rather simple and elegant, and so Casimir sought a more fundamental explanation. Casimir found inspiration in zero-point energy after a conversation with Niels Bohr, and he was able to derive the same expression from his earlier paper with Polder in a much simpler way. Casimir's derivation is the same derivation that was just covered in the previous section of this video. It is somewhat complicated, but it is very elegant compared to the derivation from the paper with Polder. For reference, it took Casimir about 2 pages of written work to present his derivation, but the Casimir-Polder paper had some 13 pages of physics and math. And that was the paper in which he derived the famous result of the force between 2 parallel conducting plates, and what is now known as the Casimir Effect. That paper was published in 1949. So far, we only have theoretical derivations, and ones that would be very hard to test, for example, because Casimir used perfect conductors. How do we know that our intuition is correct? In 1956, physicist Yevgeny Lifshitz published an extremely important paper in which he generalized Casimir's results for perfect conductors to actual real materials. For example, instead of being able to use the Dirichlet boundary conditions that are imposed by perfect conductors, Lifshitz was forced to consider more or less fuzzy boundaries. In general, the paper contained many striking results. For example, Casimir's original prediction is contained as a limit in Lifshitz' theory. This paper enabled much more precise prediction and later verification of the Casimir effect. In fact, shortly after Lifshitz's paper was published, the first experimental evidence for the Casimir effect came out. Physicist Marcus Sparnay conducted an experiment with plates in a vacuum, and his result more or less corroborated the Casimir effect and Lifshitz's theory. Sparnay set up a complicated system in a vacuum involving balances and levers to be able to very precisely position parallel plates. Unfortunately, due to the nature of the experiment, the measurements, and the technology available at the time, Sparnay's work had very high uncertainty. The paper, in fact, describes the results as quote-unquote not inconsistent with the prediction. Some of the main reasons Sparnay's work had such high uncertainty included dust particles and other obstacles between the plates. There also often existed unwanted potential differences between the plates, which couldn't even be measured with his setup, and in general, it is extremely difficult to get two plates that are entire cubic centimeters in area exactly parallel such that you can place them distances on the order of tens of nanometers apart. There was a very large margin of error, but in any case, this was pioneering work. Almost 10 years later, the first experimental evidence for Lifshitz's work specifically arrived. In 1973, physicists Sabisky and Anderson did an experiment where they measured the thickness of a thin film of liquid helium on a crystal, and their results agreed with predictions using the more general techniques derived by Lifshitz within a few percent. In 1978, physicist Peter van Blokland and the same Overbeek from earlier attempted their own verification of the Casimir effect. Instead of measuring the force between two tiny plates, where it is very difficult to maintain parallelism, they measured the force between a plate and a sphere, which made the experimental setup significantly less sensitive to error. Their experimentation provided strong evidence for the Casimir effect, bringing the experimental error surrounding the effect down to about 20%. However, the first direct, high-accuracy experimental evidence for Casimir's original result only came in 1997 when physicist Steve Lamoureux conducted an important experiment. Like Blokland and Overbeek, he measured the magnitude of the effect between a sphere and a plate, but his larger-scale experimental setup was also more stable, making use of a magnetically overdamped torsional pendulum that kept the components in an extremely stable state. Making use of more modern technology, he used piezoelectric stack translators to control the distance between the plate and the sphere, and measured the relative displacement using a laser interferometer to an accuracy of 0.01 micrometers. The absolute separation was measured by measuring the force when a known electric potential difference was applied to the plates, while they were far enough apart for the Casimir force to be negligible. His results agreed within 5% of the prediction by Casimir and Lifshitz. Even in the 21st century, work continues on the Casimir effect. In 2009 and 2011, teams led by physicists Homer Reed and Alejandro Rodriguez derived more important theoretical results. They used novel techniques to calculate, for essentially any given geometry and material, the forces from the Casimir effect. These were very general and very important results. Some different groups of scientists, led by physicists Zhu Teng and Ming Kang, published several papers in 2013, 2017, and 2021 that used a silicon chip to measure the Casimir force. And then they demonstrated different varieties of the force using chips in follow-up papers. Perhaps the most important application of the Casimir effect is in the field of nanotechnology. Here, the Casimir effect becomes an engineering consideration. It can create problems in very small systems, and it can also be utilized in very small systems. In particular, the Casimir effect is rather important in microelectromechanical systems and nanoelectromechanical systems. These systems, as their names suggest, integrate electrical and mechanical components on the micro and nanoscales and have applications across almost all fields of technology and science. One significant challenge in microelectromechanical systems and nanoelectromechanical systems is stiction, which is the often irreversible adhesion of moving parts to nearby surfaces or other parts. This can cause device failure and is a significant concern during both fabrication and operation of these systems. These types of problems can be caused by things like electric potential differences, material properties, and, as was somewhat recently shown, the Casimir effect. This understanding is important, as it could inform choices about the chosen material, for example, to reduce the magnitude of the Casimir effect. Casimir forces also have implications for the design and operation of micro and nano switches. These types of switches are used in, for example, transistors, micromirrors, and pressure sensors. These devices have something called a pull-in voltage, which is the threshold of voltage to actuate the switch, and the presence of Casimir forces can actually affect the pull-in voltage, and this is another engineering consideration because of the Casimir effect. A research team in Europe took a different angle and conducted an experiment that made progress towards creating something called a low-power nanoswitch using the Casimir effect. A low-power nanoswitch, as the name implies, is a very small switch that remains in its current state even when the power is switched off. The team used a material called silver indium antimony tellurium, or AIST, that is used in things like CDs. When heated with a laser, AIST can switch between a crystalline and an amorphous state. This, of course, affects the Casimir force, so you can actually increase or decrease the force when you heat the material, and the force will stay in its neut state because AIST doesn't switch back spontaneously. Outside of nanotechnology, the Casimir effect is also relevant in the discussion of the wetting of the surfaces of solids by fluids. When you wet a solid surface with a fluid, in certain situations, the thickness of the film of fluid changes as you approach phase transition and critical endpoints, and this change in thickness can actually be attributed to the Casimir effect. We saw this in the verification of the Lifshitz theory by Sabisky and Anderson, but perhaps a more striking exploration was done by physicists Michael Elbaum and Schick around 1991. They applied the relevant theories to ice, and they found that because of certain weirdness in the way water and ice behave, a macroscopic film of water cannot form around the ice. Instead, an exceptionally thin film of water forms, and then the extra water only forms droplets on top of that thin film. This work is also more significant than it may seem. For example, this type of ice surface wetting has been shown to play a role in the generation of lightning in thunderstorms. The vacuum catastrophe, also known as the cosmological constant problem, is the significant discrepancy between theoretical predictions and observational evidence regarding the energy density of the vacuum. As we explored earlier, quantum mechanics predicts an enormously high zero-point energy, or vacuum energy density, estimated to be around 10 to the 112 ergs per cubic centimeter when summing up the contributions from fluctuations down to the Planck scale. However, astronomical observations of the universe's expansion rate suggest a much smaller vacuum energy density, approximately 10 to the negative 8 ergs per cubic centimeter. This is a discrepancy of an astounding 120 orders of magnitude. The enormous difference between theory and observation has been described by some scientists as, quote-unquote, the largest discrepancy between theory and experiment in all of science, and the worst theoretical prediction in the history of physics. This problem arises from the fact that vacuum energy is thought to be the main component of the cosmological constant in Einstein's field equations of general relativity. The vacuum energy's extremely small observed value is crucial for the formation of cosmic structures, as a higher value would have caused rapid universal expansion, preventing the formation of stars and galaxies. Despite many attempts of varying plausibility to resolve this issue, for example, supersymmetry and various cancellation mechanisms, the vacuum catastrophe remains one of the most pressing problems in modern theoretical physics. What does this all have to do with the Casimir effect? Well, the Casimir effect is very commonly cited as physical evidence for the zero-point energy. We now have a preponderance of evidence for the Casimir effect, and if this implies that quantum vacuum fluctuations and the zero-point energy are definitely quote-unquote real, the vacuum catastrophe isn't just a discrepancy between prediction and measurement, it's a contradiction between reality and reality. That the Casimir effect provides evidence for the reality of zero-point energy is where physicists Robert Jaffe, Nikolic, and others disagree. In a paper published in 2005, Robert Jaffe makes the excellent point that the Casimir effect does not actually give direct evidence of the zero-point energy. In general, the Casimir effect can be derived without any reference to the zero-point energy, as was originally done by Casimir and Polder in their more cumbersome original derivation. He also highlights that, like all other quantum electrodynamic effects for which we have physical evidence, the Casimir effect vanishes as the fine structure constant approaches zero. This is relevant to the reality of zero-point fluctuations because it demonstrates that the effect is fundamentally linked to electromagnetic interactions between particles, rather than solely being a property of the vacuum. Still after Jaffe's paper, there was limited consensus about zero-point energy in the broader physics community. Another physicist, Nikolic, in 2016, released a proof that the Casimir force definitely does not come from vacuum energy, based on certain ideas about the quantum electrodynamic Hamiltonian. And though it remains to be seen whether modern physics in general can be understood without zero-point energy, as early as 1948, physicist Julian Schwinger attempted to reformulate quantum electrodynamics without any reference to zero-point fluctuations. Overall, while a decisive conclusion about the reality of zero-point fluctuations remains an open problem in physics, it is more or less certain that the Casimir effect specifically is not in fact evidence of zero-point fluctuations. When we derived it with reference to zero-point energy, we were making use of a mathematical or conceptual shortcut to create an approximation. The Casimir effect is a rather remarkable quantum mechanical phenomenon, an unexpected attractive force between closely positioned parallel plates, and actually, more generally, a force between any two closely positioned objects. It was originally derived in the work of Hendrik Casimir and Dick Polder in the late 1940s, and then re-derived in terms of zero-point energy in Casimir's 1949 paper, where he gave the theoretical description of what would become known as the Casimir effect. As technology and experimental techniques improved, the effect gradually gained experimental credibility. In 1956, physicist Evgeny Lifshitz critically generalized Casimir's original work, extending the theory from perfect conductors to real materials. Experimental confirmation proved challenging, with Marcus Barné's 1958 experiment providing inconclusive results due to significant technological limitations. The definite experimental breakthrough came in 1997 when Steve Lamoureux precisely measured the force between a plate and a sphere, confirming the theoretical predictions within 5% accuracy. Since then, the Casimir force has found applications in nanotechnology, particularly in microelectromechanical systems and nanoelectromechanical systems. Researchers have considered the effect to understand challenges like stiction in microscale devices. Beyond electronics, the effect has also provided insights into surface phenomena such as the unique wetting behaviors of ice. Nonetheless, the Casimir effect's deeper implications remain a subject of ongoing scientific debate. While it seems like physical evidence, it is not in fact proof of zero-point fluctuations. With reference to the vacuum catastrophe and zero-point energy, the Casimir effect stands at the center of some of the biggest open problems in modern physics. That is all I have today. Thank you very much.